Dun 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 dun. Okay, so first off, we're gonna do an unedited run of the Rube Goldberg machine, shown here. I'll let you watch that.
Oh my gosh, yes, it just worked.
And now I'll break down all the steps one by one.
Sweet. First time. Yeah, there we go.
You can definitely see those toaster elements heating up, so that's gonna make some good toast. Cool. My first physics principle used is gravitational potential. That's why I chose to start the marble run at the top, so it would have the most potential gravitational energy at the very top. Obviously, I'll come back to this point later. The second and third steps both contain two first-class levers. One is operated by my hand, and the load is another lever, and the other one is the action is this: the bottom of the ramp pulls down, and then the ball goes up. So that's another first-class lever, except the opposite direction. They're first class because the fulcrum is in the middle, and the load and the action force are on both of the sides. The ball then proceeds to an inclined plane, which then is followed by a free fall, and then another inclined plane into free fall. This is an example of the ball losing the potential energy but gaining the kinetic force that is going to then eventually go into this cone-shaped contraption. This cone is demonstrating uniform circular motion or elliptical motion, and is also an example of centripetal force because the ball is being pushed against from the outside as it goes down into this funnel. At the bottom of this funnel, the ball is captured into this cup, and then through tension force of the string, the kinetic energy of the ball is then transferred back into potential energy when this string travels up this entire contraption to the top. Here we find another lever. This won't count for anything, but I mean, levers are great and all. So then this is where it is. The inertia of this ball has made it stay still this entire time, but so it won't move. But now it has this push, and so it breaks inertia, and now it wants to start rolling forward. These dominoes are a great example of physics potentials. Now, first of all, there's conservation of energy. The loss of gravitational potential energy equals the gain in the kinetic energy. So the domino speeds up as it topples down, and then it pushes the next one over. Also, there's conservation of angular momentum. The torque produced by the contact of these two dominoes forces during impact causes rotation of the next domino to turn about over its corner. And another conservation of angular momentum. Once tilted beyond this angle of stability, the torque produced by a domino's weight causes the domino to increase its angular acceleration and lose gravitational potential energy until it hits the next one. So they are packed with physics principles. Here you can see that this ruler transfers the direction of the domino's fall, but it also has circular motion. This ruler's energy travels along the circumference of the circle and hits the other dominoes. Here we have my second use of tension force. This rope acts as a sort of a tripwire, and the force from this tension, it travels all the way down to the bottom of the machine and attaches to a pipe that you will see later. But yes, this is my second use of tension force. It probably won't work again. It's been taking a while.
The toaster's hot.
Yeah.
What, dog?
Now the center of mass of this weight is directly above this pipe, so when it gets pulled out from under this weight, the weight drops and then pulls this tension force string up to the top of this piston here. And this piston is really here to conserve the energy because I want this energy to go down into the toaster plunger from the dropping of the weight. So that's what that's there for. And there's the toaster looking as bright as my grade after this project.